In this video, we will put together the concepts of electronegativity and three-dimensional structure to determine whether or not a molecule is polar or nonpolar. In order for a molecule to be considered polar, the following must be true. The molecule has to have some polar bonds. Those are ones in which there is a difference in electronegativity between the two ends of the chemical bond. And that bond must be able to have a dipole moment. In order for the overall molecule to be considered polar, you also have to have an unsymmetrical shape, meaning that you don't have two polar bonds that cancel each other out through vector addition. The reason that we care about polarity is that polarity affects the intermolecular forces of attraction. An example of how this plays out in real-world behaviors is boiling points and solubilities. For molecules that have strong intermolecular forces, those that are typically polar, they have higher than normal boiling points. You'll also find that polar molecules will dissolve in polar solvents. A common saying is like dissolves like. An example of this is water and oil. Oil is held together via non-polar interactions, whereas water has a high polarity to it. Oil does not dissolve in water because of the difference in intermolecular forces. The non-bonding pairs will affect the molecular polarity and generally give a strong pull in their particular direction. The easiest type of molecules to determine whether they are polar or not are the diatomic molecules. An example of this is HCl, hydrochloric acid. Hydrochloric acid is very polar. The bonding electrons are pulled towards the chlorine end. Chlorine is the third most electronegative atom there is, behind only oxygen and fluorine. Because chlorine is more electronegative than the hydrogen atom, it will pull the electron density from the bond towards it, giving you a region here of low electron density nearby the hydrogen, and a region of high electron density around the chlorine. We can represent this difference in electron density in a couple ways. One is by giving deltas, lowercase deltas, with a plus for the plus end and a minus for the negative end on the two ends of a bond in which there is a difference in the electron density. Another method is using these arrows to show the directionality of the dipole. So you have a plus end where the hydrogen is, the minus end is over here by the chlorine. The arrow that is showing the net dipole between the two atoms points in the direction of the more negative side. So you have an arrow with a little plus on one end, that goes on the plus side, and then the direction that the arrow is pointing goes towards the negative end of the dipole. Unfortunately, when we are looking at molecules that are larger than diatomics, another concern comes to play. Just because a molecule itself has polar bonds does not mean that the molecule is polar. For example, carbon dioxide, the bonds between the carbon atoms and the oxygen atoms in CO2 themselves are polar. Oxygen is the second most electronegative atom there is. Carbon is a lot less electronegative. So in the carbon-oxygen bond, the electrons are pulled towards the oxygens. So in the case of CO2, each one of the oxygens is pulling electron density towards it. So you have two dipoles on the bonds, both pointing towards the oxygen, with the negative end on the oxygen, the positive end on the carbon. However, because carbon dioxide is a linear molecule, the two dipoles cancel each other out. The molecule itself does not have a plus end and a minus end. So although the bonds that make up the molecule are polar, there is no plus end of the molecule. And so the molecule itself is nonpolar. Whether a molecule itself is polar or nonpolar really depends on the type of bonds and the dipoles in those bonds, as well as the directionality of the dipoles. Another example of a molecule that has polar bonds is water, H2O. The bonds between the oxygen atoms and hydrogen atoms in water are polar. Both sets of bonding electrons on each one of the bonds is going to be pulled towards the oxygen end of the molecule equally because oxygen is more electronegative than the hydrogen atoms. Because the geometry of water is bent, the two dipoles are not directly opposite each other. They don't cancel out. They will cancel out in the x direction, but in the y direction, they will add together. Because they add together, you will have a plus end on the molecule where the hydrogens are located and a minus end on the molecule where the oxygen is located. As a result, the molecule of water itself is a polar molecule. So how can we determine whether a molecule is going to be polar or nonpolar? We had an example of carbon dioxide, which though it had polar bonds, itself was nonpolar, and we had water, H2O, which has polar bonds and is polar. The way that you can tell whether a molecule is polar or not is to first draw the Lewis structure for the molecule and determine its molecular geometry. Determine if the molecule contains polar bonds. If there are no polar bonds, then the molecule itself cannot be polar. A bond is polar if the two bonding atoms have sufficiently different electronegativities such that the electrons will spend more of their time around one atom than the other. If the molecule contains polar bonds, you should write out the vectors pointing towards the more electronegative atoms on each bond. Make the length of the vectors proportional or roughly proportional to the difference in electronegativity between the bonding atoms. Then you will determine if the polar bonds add together to form a net dipole moment. You can do this by summing the vectors corresponding to the polar bonds together. If the sum of the vectors is 0, then the molecule is nonpolar. If the sum of the vectors gives you a net vector in a particular direction, then the molecule will be polar. Essentially, when this really matters is if you have something that is symmetric and the two dipole moments are pointing towards each other. If they are pointing directly towards each other, then they will partially or fully cancel each other out. If they fully cancel each other out, then the molecule is nonpolar. If they only partially cancel each other out, then the molecule is either partially polar or fully polar, depending on how much the dipoles of the bonds cancel or add together.